Welcome to this tutorial. Thank you very much for participating in this conference. This tutorial of Internet of Things, models, protocols, and platforms will given by engineer Gustavo Giannattasio, which is MBA, PMP, is a senior member of IEEE. He's a IEEE Regional Latin America Director. He's member of the board of the IEEE Technology and Engineering Management Society, member of the board of IEEE Internet of Things Standardization Committee. He is also an IEEE Smart Cities Initiative member of editorial team and invited expert to ITU Smart Cities Work Group. He is chapter chair of IEEE TEMS in Uruguay and chapter chair of COMSOC in Uruguay. He is session chair for COMSOC in ITU I-14G, and he's a technical program chair, IEEE International Smart Cities Conference Trento in IT. This tutorial, participants will have access to the development models and platforms and a technological update that includes protocols, communications, with emphasis on 5G and low power wide area. Information will be available on options to venture into various areas of application development, and some relevant protocols for IoT will be compared after the first part of detailed architectures. Novel protocols like QYIC will be detailed, and the importance of the DTLS protocol for IoT applications using UDP. Finally, a chapter on IoT security and details on the IoTA architecture will be architecture of distributed ledger for IoT applications with examples on the electric market and industry 4.0 will be presented. Please feel free to make questions in the chat, and those questions will be posted later to engineer Gustavo Giannattasio. So, Gustavo, up to you.
Thank you for the introduction, Irene. Thank you very much. This is a glimpse of IoT, and will take about 1 hour, a bit more. And my suggestion is, if you like to take deep dive into IoT, there are some tutorials that you can follow here, 110 tutorials in Internet of Things. And this is the program for IEEE Blended Learning. It's an online 30-hour course of all these kind of activities on the IoT arena. So don't be surprised. This is a jungle, and like the IoT protocol is also a jungle, so we cannot go to every species here, and we will cover some of them, the most important ones, according to some criteria. Going simple, IoT has 3-4 parts, like the sensors, the gateways, edge or fog computers, the cloud services or the network, and the data center. And finally, hidden by my face there, I don't know why it's there, there are users and administrators. The red line represents proprietary architecture, and the blue one represents the general public use in cloud services. Both of them are possible architectures for IoT. Some organizations you already know, I won't take much time on this. You can read here, they are all quite common, and you can go there to get actual information. Some alliances have some classification of the layers. It's a bit different from the OSI layer, network, access data, application, etc. So we have here one example of the Open Mobile Alliance with application, web transfer, and internet. And I'd like to remark the quick protocol in between the UDP and TCP. I assume you all know what UDP and TCP means, but nevertheless we'll explain in detail why this quick square is there. Going back to the application layer, transport, network, data link, and physical layer, some of the protocols we will cover, you can see there, 1M2, 1M2M, 6 low pan, quick, etc. Another reference is the Open Standard Reference Model, where you can find there many of the protocols that we're not going to cover, just the market with red circles. So this is just 1 hour tutorial, so we cannot go in every detail of all the protocols that are used. This jungle will take just few samples. One of these is the ISO ISC 30141. It's an ISO 6 model that contains some specific domains, like down below the sensors, the equipment, then the sensing control, up there the service domain, and the user domain. And the importance of this model is there is a company called SD Chain that argues that they comply completely with that model, and they put the blockchain distributed ledger on top of this. So there is one example of integration between standards and new technologies like blockchain. So if you want to go deeper, SD Chain is the answer. IoT firmware is pervasive in the world, especially in Europe, Asia, and also in America. Uruguay is a good example. We have 2 nodes for firmware. One is the municipality and the other one is Antel. You can see there below the resources of the city, the device management with IoT agent marked in blue, and then the model following the OMA, Open Mobile Alliance data model. So it's completely standard, and more important is open source. So this is a clear platform if you want to go into IoT project. So you can plan to use this IoT firmware architecture. If we go deeper into the IoT firmware, it's based by the Firmware Foundation. It's a non-profit organization based in Germany. And we can have here in red market there 2 very important models. One is the IoT agent. We have here from the left any IoT device going to an IoT agent, then goes up to the broker. The broker is very important because it consolidates all kinds of sensors and produce just one typical information that the users want to have without the need to go to every particular sensor. The most IoT stack used there uses some protocols very common like IPv6, IPv4, etc. And HTTP, everybody knows what HTTP means. MQTT, well, we talk about this. COAP and Sigfox. So we'll talk about all these protocols that go into the IoT agent to get northbound API to the complete platform of the firmware. Some of the protocols used in this IoT are on the right. So we have transport protocols like HTTP, MQTT. The payload may be JSON, ultralight, and there is any combination to have 4 kind of mixture of those previous protocols. I mentioned firmware because it's very important for the new technologies. And you can see here there is 2 modules included in the firmware architecture. One is the IOTA service with fully details will be given at the end of this presentation, and the Ethereum that many people that is in the blockchain business knows what's that. ETSI, the European world-class standards, also have a model We will not go deeper because there are other things that are more important than specific architectures, because there are so many architectures to discuss, like the NIST. NIST, you just take note on these standards. Uh, Open IoT, services and components. We have here down below the sensors and up there the application plane. Every interaction is included there, and you have just to go there, and Open IoT is a very common platform to use in IoT. The International Telecommunication Unit also has many things to talk about IoT. So you have there some standards, and there is now a working group that has standardization of smart city into IoT working this year, and you will see documents very soon. IIoT, Alliance for Internet of Things Innovation, is another platform. The European Research Cluster for Internet of Things, especially concerned on the Internet of Robot Things, IORT. It's about robotic actuator executors, etc. Then we reach IEEE. We see here many of the standards related to the IoT arena, like interface, air interface, metering communication, especially on the smart city. There are so many standards, and also in the Internet of Things you see on the left the P2413, the architecture of IoT. This is very, very important because it's the core of the standards. IEEE started very early with some implementation with machine to machine. One is called 1888, and you have there in the right, you can compare the ETSI M2M with the IEEE 1888. This is a rather old architecture. You see 2011, 2009, and much water has been through the bridge. So there are many other standards, like 2413. So many companies working on that in the Standard Association. You can see there, Sigfox, Siemens, Intel, so many. Actually, 2413 has three main lines. One is the architecture framework for the Internet of Things. The other one is the reference architecture for smart city. And the third one is the standard for a reference architecture in power distribution. It's very important for power and engineering society, I think. This is another view of the same standard, 2413, that applies to many different things like smart grid, smart buildings, smart cities, smart healthcare, etc. ISO and IEEE work together. They have a common standard called 40010, and it's about all the sequence needed to relate stakeholders with the architecture of the system. IEEE is very important in the IoT arena because they decided to introduce the concept of roof computing. It's a standard, 1931. That is, this is a table here. You can compare the roof with the fog and the cloud. Everybody knows about the cloud on the right. In the middle, there is a trend about the fog, and in the left is about the roof computing. So the roof computing takes care of a few meters of distance, millions of numbers in deployment, and it's useful for all kind of IoT applications. And most important is the cost is rather low compared to the other architectures, but cloud is also needed, of course. Roof can be integrated with blockchain. You can have a peer-to-peer trust in the cloud, so it's a quite interesting feature of this roof computing innovation. Talking about blockchain and IoT, IEEE has many standards related to the blockchain, and on the left you can see there the application like trading, like billing, like security, grid management, etc. So there is one initiative called called the Blockchain Transactive Energy Initiative that you people from the Power and Engineering Society and Smart Grid IEEE and also the CGRE will be interested in going into that area. This is one example of different transactions for different solutions like transaction of energy in orange, financial transaction in blue, and data recording. So in different things like distribution, retail, transmission, generation, there are different applications for this standard. Also, we can mention the Internet of Things World Forum. It's very important. They have layers from collaboration, application, data abstraction and accumulation, edge computing, connectivity, and physical device. This is not related with the ISO model, but this is the specific levels for each of the process needed to get data from the devices to the process. So the business decision will use applications and analytics to get data integration and visualization coming from devices that go through the physical device, connectivity, and edge computing, and then provide data for operational and IT sectors, completely different but related with this same architecture. Not to mention, there are many other IoT platforms like Watson, Microsoft Azure, ThinkWorks. I like to mention Samsung Arctic because this one is integrated with one of the blockchain solutions that UTE, the power utility, has going into agreement. So the household appliances will have the capability to interact with the UTE using this Arctic model. Siemens, not to mention, has also the MindSphere, Honeywell, Azure IoT. Yes, this is also very important to have consideration that IoT edge devices have to go through user management, passing some processes that are detailed here in this slide. Azure IoT provides from the sensor to the cloud all the solutions needed to make a turnkey solution for IoT applications. Amazon, IBM Watson, ThinkWorks, Bosch, Carriot. You will say, there are so many. Yes, there are so many. And each one depends on what you want to do. In Argentina, for instance, the municipality has been using Microsoft. And in Uruguay, the municipality has been using the fiber. So each organization has the duty to select the best option of their architecture. Now, we go to the IoT protocols straight ahead. And this is the core of the presentation. So pay attention and fasten seatbelts. This is going to be a quick view of all the protocols we can cover. If you look at this layer and protocols comparison table, you will see that there are two very important because they use something called UDP and DTLS. So this is a very important distinction between all the architectures that don't use TCP because it's too heavy, it's too choppy protocol, the TCP. So if you use UDP, it's much better. So there are some solutions that apply UDP as transport. Another concept we have to consider is how do we interchange information, either server to client or publish to subscribe. The main difference you see there in the picture is there is a broker. The broker is who takes care of all the client requests and make the consolidation of all the data, so no client has to go straight to the server but go to the broker. The broker makes all the functions needed to classify and make orderly data available for the users. Some of the most important protocols are summarized here: MQTT, MQTT for sensor networks, and Restriction Application Protocol for IoT devices. We will go in few details immediately. XMPP, XMPP for IoT, and AMQP are also messaging for IoT devices. So we must understand how they are used. MQTT is very, very common. It's low overhead. It's a model publish subscribe that we mentioned a few slides minutes. And there is a broker server that publishes all the data that is subscribed by some of the people. Here you have the explanation of the publish subscribe feature of the broker. The publisher has up to here in this slide 4 different publications, and the subscriber can subscribe to any of them. Like the upper subscriber goes to topic 4, that can be, for instance, temperature, but the subscriber that is below has topics 1, 2, and 3 together. Could be temperature, pressure, and humidity. And there is no need to go to the special sensor, but to the broker. The broker takes care of publishing every topic to the subscriber that needs just that topic. For sensor networks, there is a problem because they don't have TCP/IP transport layer. They have some protocols different, like ZigBee on top of other layer. So MQTT, which is based on TCP, cannot go directly to the sensors. So there are some brokers inside the TCP-based network that can interact with all the sensor nodes. So this is architecture for MQTT-SN. It's not much known, this protocol, but it's very important for IoT. In this gateway, you can see that non-TCP/IP networks can interact with MQTT broker and normal TCP networks in 2 different ways: aggregating or transparent gateway. The drawing on the right shows the difference. MQTT uses TCP and security from TLS. TLS is very chatty, and also TCP is very chatty. So we can use MQTT, but we have to pay attention on how much bandwidth we need if we use a lot of sensors, and the delay from the publication of the information to the reader. So we'll see later how this can be solved. Constraint application protocol is in between UDP and application. It's very important because it uses UDP. So there is no need for all the chatty protocol that normally TCP has. It's a model also type public subscribe and supports different transfers like block transfer, discovery, and caching. It's a model request response. So you see how light is the messaging. We have here in the left the HTTP request normal with so many handshake operations. And on the right, we have the request response that to get information from the client about, for instance, the pressure is just one command, get pressure, and the server replies with the application 22 kilo pressure. XMPP is open standard for messaging, but for many other different things. It's used for protocols since 2011, and it's now consolidated in the RFC 7622. The characteristic is There is a discovery. It uses security TLS, so this is not good. And the transport is TCP. It's also quite complicated. So XMPP has limitations, and we will show later how this can be overcome. There are different domains, so we can have different gateways for XMPP, either via SMS or by SMTP servers. And both can go to XMPP layer through internet. One beauty of this protocol is it can be using the Red Node development tool. This is a very important graphic tool that you can connect inputs with outputs, and you automate all the programming via this Red Node open source tool. Advanced message queuing protocol. This is also used in the transfer of information from IoT devices and can be encapsulated into a TLS. That is not so good. Could be inside TLS or could be inside a web socket tunnel. So it's a widespread use, but remember, TLS is not so good for taking information because of the time it takes to the handshake. DDS Foundation is a middleware protocol developed by the Object Management Group, OMG, and integrates all together with low latency, extreme reliability, and mission-critical IoT applications. So you can see there in the platform, you see in the middle network UDP. That's important. It also supports TCP, but UDP is one of the systems that can have profit of the low shaking hands interaction between client and server. DDS has a domain, so publication of topics like metering or wind speed or generation can be accessed by subscribers that get just speed, power, phase, etc. in different domains and do not interact to each other. Just they have their own system to get information they want. It's widespread use in the power systems. They can have also different layers like a control domain, central domain, administrative domain, and machine domain. Machine domain is what we are concerned, just machine devices, sensors, etc. But all the other domains are important, like monitoring, alerting, and analytics to get big data integration. Finally, we reached the table I wanted to show you. We have two applications, very important, with DDS and COAP, that both use DTLS. DTLS, try to remember, is very important because of the low latency they have. Also used in the IoT arena is the 6LoWPAN, QUIC, and DTLS. 6LoWPAN is IPv6 over low power, so it's very special for IoT. Many developers should get information in this implementation, and responds to an RFC specific 6282, and it has three functions very important: header compression, packet fragmentation, and forwarding. So this can have very important features to be used when we need IoT devices in an efficient way. The header stacks can have different combinations depending on whether you want fragmentation or you want multiple hops, whether you want both or one of them. So in this slide, you can see how the header is varying according to the need of fragmentation and multiple hops or not. we reach the best point of the DTLS-TLS discussion. So on the right we have MQTT with TLS and TCP, and on the left up there we have the co-op DTLS and UDP. Then all the normal internet protocols like IPv6, LoWPAN, etc., and the device. And why is this distinction important? If you look inside TLS and DTLS, you don't see much difference, because DTLS uses almost all the resources that TLS was invented, was created. So where is the difference? In the case of TLS, it needs to be transported by TCP on the right. Then, in the drawing up at right there, you see the red is just the source and destination port. It's very important to reach information from one source to one destination, but there are in blue market all the chatty handshake with sequence number, acknowledge, etc. All this takes a lot of time, and maybe this is not the best solution for IoT. But if you use the TLS, that was quite similar to TLS, but it is supported by UDP, so we have the same source, destination port, and then the data, nothing else. So the transaction is quite fast. The latency is very small. So if you use IoT in large quantities, please use DTLS. One solution to overcome all this is a new development called QUIC. QUIC is a protocol for using HTTP3 over UDP to reach the network without using TLS and TCP. Why is this so important? You can see in the right how a client and server interchange information with handshake, and finally the data transfer in red. So if you go to the right in this drawing, you will see the handshake is minimal, and then the data transfer is just as soon as possible. Yeah. So it's very important to consider QUIC for IoT application, especially if you have a large number of devices. This is the same feature with some video. Okay. Going forward, lightweight end-to-end and so on. Lightweight end-to-end comes from one M2M that has a consortium that has support from ITU, IEEE, Open Mobile Alliance, IETF, many. So they define some common services that are used to get information from the sensor to the user of the application. Then we have application entity, common services entities in different layers. There is also a lightweight end-to-end. The lightweight end-to-end use co-op and DTLS. So you see, this is important to consider, because for lightweight, that is light protocols, it's necessary to use DTLS security. There you have the lightweight end-to-end supported by the industry has two main features to comment: the co-op bandwidth optimization and DTLS security based on co-op. So up to this point, we know there are many protocols. Some of them are noisy, chatty, with high latency, and others are very light and efficient. The case is we must use co-op and DTLS to make sure all the information is transferred as soon as possible. Well, for routing, there is not just OSPF, there is a network RPL. RPL is according to RFC and has the capability to be installed into constrained devices, that is, small sensors that have a small battery, CPU, not so big, and so on. So the RPL is based in the directed acyclic graph. Remember these three words, directed acyclic graph. Will be used in a blockchain system, and it's also used for routing information between sensors in the network layer, right? Finally, other protocols are SOAP and WebSockets. You have there the interaction between all of them, and this is quite common in the layers that use REST and SOAP. Going to a more familiar for the radio frequency people, we talk about radio frequency standards like 802.15.4. Yes, it supports different topologies like star, mesh, cluster. The data link uses time slot chain hopping. That is, the time slot is moving, so it's a way to synchronize and guarantee collision-free of the information. We have also the AH, 802.11ah. It's a very common standard, quite fast, but it's not the fastest. And it's used mainly to concentrate information from different locations, and it's quite fast. But now we have the AX on Wi-Fi 6 that is much more powerful than the previous 802.11. It's 4 times better in dense environments. So if we have many cars or many garbage containers, it's important because it has a very quick response and much faster throughput. So it can send a lot of information at the same time. It's reduced latency. It's with improved security. So this is the future, Wi-Fi 6. If we compare with previous, you see there the speed 3.5 giga, Wi-Fi 6, and Wi-Fi 6 is 9.6 giga. In addition to that, there are much more gigabit per second per device in the final version that is going to be released during 2020 and 2021. So pay attention on Wi-Fi G6E. Somebody wants to compare with 5G. So we have to consider that carrier managed is for outdoor, and for indoor we use Wi-Fi. Now we go to Narrowband IoT and LoRaWAN. LP1 is a technology that has open source since 1 year. It covers a quite range of speed and distance. And there are 3 main players in this. Sigfox, Link Labs. That is for LoRa. There is another one completely different that is for Sigfox. The frequency bands are there, 900 and 800. We have in this particular country both frequencies in operation. So the beauty is they don't need to get a special license and license to be used. Sigfox is also available in our country, and it uses also radio frequency chairs. LoRa needs a cloud server, so it's not just the device that is LoRa and the gateway. We need a server. This server, called network server, makes the difference between LoRa and LoRaWAN, because LoRa is a physical layer and LoRaWAN is the communication protocol and the architecture. So we see there MQTT, remember WebSockets, and the end nodes on the left going through gateways LoRa to a network server. So somebody has to put a network server in service to get the client application to access the data. Not just the sensor with the end node with the LoRa, but it's needed a network server. Semtech is the creator of this technology, and the modulation is completely different. The 802.11 whatever, AX, H, X, etc., use direct frequency spread spectrum, this on top. They use specific frequencies, and in each frequency there is a modulation called direct sequence spread spectrum. LoRa use what is called chip spread spectrum. There are pulses that go in frequency, in time. They change according to certain modulation. This modulation makes the frequency change in time, going with an up slope, and then the symbol comes, then goes again with up slope. So the way to discriminate this is to get where the frame starts and where the data is. And this example shows where there are some data coming in the binary and where is the rest of the frame. There is a preamble. You have here the frequency axis on the right and the time going down in the figure. So first there is a preamble to make warning, hey, be careful, there's going to be a frame limit. So in number 2, you see 2.25 down chairs, that is the frequency going down, and then comes the data. So how do you extrapolate the data from these up and down frequencies? You have to complex conjugate the data. If you complex conjugate, you get a real version of the value, and then the data is discovered by making complex conjugate with the information coming modulated by the frequency and the up chirp and down chirp log. This is a modulator. It has normal things. The datagram and the features are the modulation, the encoder, and the decoder. All this is done by the protocol LoRa. It uses different bandwidth, and there are some spreading factors with each, the shortest time and the longest time. Each step, the factor doubles the time to Earth to transmit the same amount of data. You have here, according to different spreading factors, the bit rate, there is not much, and the sensitivity. Sensitivity is very important because you see it's too low. The dBm are too low, so it can work very well in presence of noise. The data rate is not so more important, but you can see up to 5 kilobits per second or 12,000 kilobits per second, depending on the data rate. Who supports LoRa? All these companies support LoRa. Symphony Lab goes on top of LoRa. It's a development that can have all the necessary applications to take information from LoRa networks. This is a calculator to show the distance. In this case, if the transmit power is 20 dBm and the attenuation of the system is 10 dB, and etc., type of antenna, phase margin, you get coverage of 6 kilometers. So it's quite long range reach. So In the beginning, when narrowband IoT was not available, the Symphony or the LTE-1 with LoRaWAN was the solution. And you can have here just a way to compare narrowband IoT with the LoRa. Battery life, quality of service, latency are quite different, but they complement each other. When there is no narrowband IoT, well, the LoRa is the best solution. There are many other LTE-1s, Touch, Jenny, RPMA, Bluetooth, Zigbee, etc. And if we compare the LTE-1, we have there in the left, Sigfox, LoRaWAN are the most common, and the distance and the frequency and range. You see there in rural areas, Sigfox up to 50 kilometers. That is a lot. And in urban area, 10 kilometers. Well, LoRaWAN is much more. It's 15 kilometers, and in urban area is 2.5 kilometers. So we go to 5G now, narrowband IoT. There are different releases by the 3GPP organization, and release 17 is just in evolution and not completely deployed. This is the chart of the different ongoing releases. We are today 2020 and release 16, and the 17 is in preparation in some of the milestones suffer risk of being shifted, mainly because of the pandemic. I think there are a lot of developments that have to be postponed due to the pandemic. 5G protocols use HTTP. We can use QUIC. Remember, QUIC is important because of the lack of the CHAPI and the UDP used for the security. REST, it's also possible. Some variants, we have the LTE-M and narrowband IoT. In our country, it's used narrowband IoT, not LTE-M. They're quite similar, but the duplex mode is a bit different. The characteristics of the technical aspects show that we have standalone dedicated channels and could be in the guard band between 2 LE or in band inside LTE band. You see there the same schematic about the narrowband IoT carrier and the rest of GCM carrier. So they coexist. One of the important things of narrowband IoT is it has a class of services that you can save battery and increase the speed of the transfer according to different classes of services. With other radio frequency service provider operation, this is quite difficult to handle, but with narrowband IoT, it's quite simple. There are some kits to test the narrowband IoT, both in flavor, kind of gateway between LoRa, Zigbee, Bluetooth from one side, and narrowband IoT on the other. So this is done by, you see there the sign Intel. Another important thing for the use of radio frequency is the embedded SIM. The SIM has been changed, and now you can have electronic SIM that has areas for operator and for application domains. And this is important because we can have different operator domains, and the same SIM is used for any different operator. You don't need any longer to go to change your sensor if you go to an area with operator A and go to another area with operator B or a different country. With one single standard electronic SIM, you can have both operators covered, and there is a handshake to configure the system, and the electronic is much simpler because you don't have to open the sensor to change the SIM, and it runs in every country of the world, provided they support the electronic SIM standard. This is the electronic SIM standard suggested by GCMA, that for provisioning you need the manufacturer, you need the one certificate user to make sure this is all legal. Then you need a subscription manager, and finally the mobile network operator. All interact together, and they can program, yes, the electronic SIM. So you don't need to use different physical SIMs, but just one electronic programmable SIM. Now we're reaching the last 15 minutes very quickly. How IoT influences the decision on security to be used. We focus on the Internet of Things, but before, IEEE has a blockchain, and TEM Society has a lot of information on security and blockchain. There are a lot of standards in IEEE. This is not just the only one. There are, I don't know, nearly 50 different standards for blockchain. And we have to cover different things when you use sensors, like identity, to check who, what, when, how, the origin of the components. We have to authenticate transactions. And we have to get IoT management, like vehicle-to-vehicle or Industry 4.0 interaction between machines. There are all different needs, and IoT is not just simple as a monetary transaction that you do with blockchain, because you cannot wait 10 minutes to get a response. So distributed ledger is a way to store all the information so it cannot change, it can be secure, and the platform are basically two, general and focus on IoT. In the focus on IoT, we have the special one distributed ledger for transaction machine to machine and for IoT management. We will cover the red dots. Why do we need blockchain? Well, there are different sensors. Each one solves a different problem. Some of them just tell temperature. Other ones act on a solenoid valve. Other ones take both transmission, receive information, and take actions. And finally, there are autonomous. There's a mistake there. And the complexity is completely different. So the IoT presents different restrictions if you want to use distributed ledgers, like scale, security, update, etc. What about the scalability? Everybody thinks in many sensors, but it's enough just the number of sensors we have to consider when we say scalability? No. Number of sensors is one of the issues. Latency. How fast can we get information? As soon as we can. How many transactions can we process per second? We need a lot more. The bootstrap time, so the sensor is in operation, takes some time. So this bootstrap time can be minimized. And finally, the cost. We don't have to pay much cost for every sensor because it will be impossible to sustain thousands of sensors. We have to pay for each of them. Every transaction, every half an hour, we have to pay a transaction. That is impossible to consider. So can we achieve the minimum and the maximum of this multifactorial IoT scalability? Well, depends on what kind of security we want. If we think in sensors only, it's just on the left, it's the tip of the iceberg. There are a lot of systems that involve in the end-to-end from the users themselves, the operation, the platform, the network, and the edge device that have to be secure. So the security threat is quite complex. We cannot stop by thinking just in the sensor itself. It's an end-to-end, there is no discussion, from the sensor, using cryptography, using everything we can, but we also have to cover security in the gateway, in the networking, in the cloud, and the applications. All have to be secure and managed. Somebody thought, can we use blockchain security? Of course we can. And it's very useful because we cannot delete a measurement, we cannot change it. And how we do it? Well, there is a function called the hash that if you change just one single character, the next chain, in the chain, notice that the hash has changed. So there is a fake message, so it's not real. But there are some additional problems. If we have a record, we have to make a block, and then we can make a chain. So this will take a lot of time. And the question is, will this be optimal for financial transaction? Yes, of course. Will this be optimal for transporting things in ships and planes? Yes, of course. But what about IoT? What about if a car needs to talk to another car, or a machine talks to another machine? Maybe this is too complex and too time-consuming. This is what I call how to explain hash is important. We have a phrase with one single change in between, and the function hash is completely different. So everybody noticed that someone has changed the message because the hash is completely different. There are some standards. Some of them are used like 2, 5, 6 digits family, and there are others like the Troika that use a ternary machine, that is computer using base 3, not just 0, 1, but 0, 1, and minus 1. So base 3 machines. This cryptographic function has a live version that can be embedded into a sensor. So we can have from the start inside the same sensor all the capability to have the cryptographic function. So one of the solutions is this. This is not for financial transaction. This is just for other things like IoT. Finally came the elliptic encryptions. So the elliptic encryptions is a solution, but came the post-quantum cryptography. So now with quantum computers, are all these encryptions safe enough? Well, somebody showed vulnerabilities on those elliptic encryptions, but the one-time signature is very important. This is an example we cannot explain in the time we left. But the idea is that we can check the signature in a heavy use of hash function. We generate a private and public key, and if they are the same, the signature should be correct. This is the process. So you see there in the video how a bottleneck is formed when we use blockchain. So if this bottleneck is for financial transaction, may be acceptable, but not for a car when moving from one corner to the other, and the other car needs to get information. Also, the blockchain uses miners to get the validation. And the miners are very heavy data centers consuming a lot of energy, and they charge. So do we need charging every transaction for IoT? The idea is we don't need. So DLT is a good solution for IoT in the case we can secure authentication, secure transaction, avoid any different charge for every transaction, and There you see interaction between the different cards. So some of the DLP are used for the Scratch architecture, and some are good for classic cyber systems. The keyword for blockchain is the consensus. There are so many different consensus. You will see all try to get the double spending attack and the network failures. And some solutions use a parallel network to solve that delay. But finally, IOTA, through the work of Sergei Popov, suggested the use of, remember, the direct acyclic graph. It's a theory topological that includes the transaction from a new transaction to validate two previous transactions. So that can be put into a sensor. So the properties are latency is small, we don't need any miner, no cost, highly scalable, and it's open source. So it seems to be a very good solution for IoT. These are some, I'll take 5 more minutes because we started 5 minutes late. And this is a sum of examples of technologies that use IoT capabilities. So the final decision is why we use Tango IOTA, because we don't use blocks. So it's different from blockchain. No transaction cost. Infinite scalability. We can have many transactions because they run in parallel. The consensus is right. So we can port the consensus criteria algorithm into the sensor. We can also have sharing that to make parallel processing of different transactions. This is one simulator. 5 more minutes, please. So the triple restriction, that is, you can have just security, you can have scalability or decentralization. In blockchain, you have to choose just one of the sides, but with this technology, you can solve 3 of them at the same time. What happens in the future when quantum computers are prevalent and try to decrypt hashing mechanism and encryption? Well, IOTA seems to be more resistant because of the use of the one-time signature. That is also a key distribution using quantum and signature. This is one of the final slides. You see here a summary, the blockchain architecture in the left, and down in the left, the direct acyclic graph. So no bottlenecks. So IoT is a good choice for this kind of technology. And this is quite intense. We should avoid all this part. And I'd like to finish with this. And where do we put our encryption and cryptography for this architecture? We can have it in the server, we can have it in the edge computer, or we can have it inside the same sensor. The beauty of this technology is we can put all the encryption inside the sensor. This is one example of a company that put all that kind of encryption inside the sensor. This is another example that put also encryption on the same sensor. And to end, I would like to show some applications. I just like to mention this one. Maybe some of you know this application. It is not exactly Ethereum, but just changes from Ethereum. This is hybrid because it can support Ethereum and IOTA. And this is for smart grid. So the world is full of applications of this new technology. This is interchanging balance in energy in Holland. This is for sensing garbage containers. This is for temperature. You see ported the distributed ledger inside the sensor. And there is also application for smart cities, for cars, for health, for supply chain, for agriculture. This is in Norway. And how we do it, and we finish. We can do it very simple using Amazon Marketplace. We can have testing sites there, very inexpensive, and much more easier is if we have access to firmware. There are IOTA services and also Ethereum services integrated into the firmware already existing in many administrations. All right, there is more, but we cannot continue because of the time. But just remember, automotive industry will use IOTA as a standard for industrial IoT, and digital twin for industry 4.0 are also using IOTA. So sorry for a small time we had, and I'm open to questions.
Hello. Okay. Thank you very much, Gustavo, for your presentation. Maybe I have one question, which is related to security, since obviously this IoT will be in everyone's house very soon, if it's not there already. So security, I think it's a big issue, and even though you mentioned that there are many features that are already considered, what I don't see, maybe you can tell us if this is already mature, is a common standard for security, like a layer, like we have application layer and maybe security layer for all this, so that our fridge won't tell the neighbors the time of our breakfast, for example.
Yes, there is one. It's the Industrial Internet Consortium. They have a complete framework for all the security. It will take about 20 slides and covers from the security of the sensor, security of the edge, security of the cloud, everything together. And believe me, Industrial Internet Consortium is the place to go for. If you want, I have a presentation. I can put it right now. So the answer to your question is yes, there is a standard, and it was developed by the Open Internet
and so
Consortium.
The market has applied that standard already, or everyone is doing by his own?
At this moment, everyone is doing what they can, but the standard is in place, and it's been approved, and we hope in the near future many devices can tell when you purchase something like a watch to check your heart, what kind of standard they use. If you purchase a watch to check your blood pressure and nothing says, there should be nothing there. So there will coexist sensors without any standard regulation, and there will be others with standard regulation, like the things they use for the petrol companies. They have a lot of standards, otherwise there could be dangerous situations, like in, some accelerators in Iran was hacked by some people, and it was a terrible problem some years ago.
We have also another question about security here. Victor is asking why did not use IPsec protocol for security?
IPsec should be used in part of the network. So you cannot use IPsec from the sensor to the end user. There is an end-to-end, and one of the networks has to use, for instance, VPN. So if we go from one sensor through the service provider, through your server and your application, who's taking care of the middle between the device and your computer. So the service provider. The service provider has to do IPsec, VPN, etc. So as far as I know, all the administration, when they gather information from sensors to the central site, they have also VPNs from the public company. That's the case of Montevideo Municipality, for instance.
Okay. Perdimos el audio. Wait
No.
Hello?
No.
Gustavo?
Sí. Hello.
No, okay. Well, if there is no other question, thank you so much, Gustavo, for your presentation, and thank all participants for being here. We will see you on next track. Thank you very much.
I'd like to say a final word, if you let me.
Okay.
Please remember to go to this place. One moment. Remember this one. Remember this My Learning IEEE blended learning. Well, there are plenty of courses, 30 hours in length, 30 hours, covering IoT, covering many things that in 1 hour it's impossible to cover. Thank you very much.
Okay. Thank you, everyone.